You might be wondering, why are we learning these things about two parallel plates, particularly infinite parallel plates? And I'm going to attempt to answer that question and give you some examples that will apply this. And it's already a device you are using in the lab that's due this week. This is the symbol for capacitor. A capacitor has two parallel plates. They're usually very close together in practice. There are different ways to engineer them that push them really close together and wrap them all up in a little tidy package like what you used in your lab. But they are two plates, and each plate has a wire associated with it. And when, for instance, a capacitor is brought near a battery or charged up by a battery, you get positive charges that occur on one side and negative charges that occur on the other side. Okay, and that's what you see in lab. And once you take the battery off, take it away, you'll find out that the capacitor then has the battery's voltage across it because of the charges that were placed there by the battery. Before the battery was there, these charges that you see here didn't exist on this capacitor. But notice also that the capacitor is net neutral. What do I mean by that? I mean there's just as many pluses as minuses. The pluses are why the minuses are there. They attract them. But if you add them together, there won't be any net charge on the capacitor. But we say that the charge is placed on the capacitor when we put plus charge on one side and an equal amount of minus charge appears on the other side. Okay, so that is the capacitor. And of course, it's really just two parallel plates. And what that means is, ideally, the electric fields just go like this. They go from the positive plate to the negative plate. And you do have a little bit of this kind of thing happening on the outsides. You get a little bit of electric field that isn't perfect because it's not an infinite set of parallel plates. But we're going to assume that they are essentially perfect or infinitely parallel plates, and that the electric fields go directly from one to the other one, which means, of course, that the potential field lines are high on one side. They're highest right here, actually, right on this plate right here. It's where they're highest. And then they go down, but those are all equipotential lines. Okay, and then at this plate, they're at 0. It's typically how we do it for a capacitor. All right. Now, what's interesting to us is how much charge is on the capacitor. So how many of these pluses and minuses do we actually have on the capacitor? And I'm going to give you an equation right now that we'll be talking about a lot for the next little bit. It's the very useful equation regarding capacitance. And it basically says that the amount of charge on the capacitor is equal to the size of the capacitor, which we'll talk about. That's something called the capacitance. And those are the values you're seeing in lab. But you multiply that capacitance by the voltage, or the potential difference across the two plates of the capacitor. That's this, plus minus V across the capacitor. Okay, so the bigger the voltage, the more charge there is on a given size capacitor. The more charge, the bigger the voltage there is on that capacitor. I remember this equation by thinking that the charge is equal to Chula Vista. It's a city in Southern California that some of you might know. So that's how I think about this equation. And this equation basically relates, as I said, it relates the amount of charge to the capacitance. And the problems we've been working on actually demonstrate that. And I'm gonna step you through how I got this equation in the next little video. But this is an important equation to think about regarding capacitance. And the capacitance, I should state conceptually what it is. It refers to the ability or capacity to store charges. When I say storing charges, I mean both plus and minus at the same time. So the capacitance, the bigger the capacitor, the more charge it can store for a given voltage. So you can think of the capacitor as kind of like a cup, and the charge is kind of like water. The bigger the cup, the more water the capacitor can hold. All right, so that's a little conceptual idea and a little equation that relates capacitance, and we'll do more with this in just a little bit.